So in the last class we have discussed the degree of freedom, where we have find out the different degrees of freedom, and what are the degree of freedom is that the number of independent terms present in the expression of kinetic energy of the molecule. Now moving ahead with this concept, we have arrived to the concept of law of equipartition of energy. What it states that according to this, the average kinetic energy associated with each molecule and with each degree of freedom is half kT. And what K is? K is the Boltzmann constant. So the K can be defined as R divided by the Avogadro number, and that this R is the gas constant. And for the case of ideal gas, we know R is 8.314 kilojoule per mole per Kelvin. So because now, according to law of equipartition of energy, if this is the energy associated with the degree of each molecule and which each degree of freedom, then we can find out what is the total internal energy present inside the system. So for the case of monoatomic gases, the kinetic energy is, we discuss, is 1 by half m Vx square plus half m Vy square plus half m Vz square. But according to the law of equipartition of energy, this becomes 1 by 2 kT plus 1 by 2 kT plus 1 by 2 kT, and so this becomes 3 by 2 kT. So from this, can we conclude that if I have to write the kinetic energy of the molecule in terms of the degree of freedom, so can I write it like this? Can I write it like this? So this is the degree of freedom divided by 2 kT, because we have arrived 3 by 2 kT. 3 is the degree of freedom for the case of monoatomic gases. So can we write it like this? So if we write it like this, I can use different color to make you aware. So is F by 2 kT. So that is of one molecule. So this is the kinetic energy of one molecule in monoatomic gas for any gas which has F degree of freedom. The kinetic energy of a molecule whose degree of freedom is F is given as is F by 2 kT. So that is of one molecule. Okay. So now if I want a kinetic energy of 1 mole, kinetic energy of 1 mole of gas, so that is nothing but kinetic energy of molecule multiplied by the, so in 1 mole of gas we know that 1 mole of gas has Na this number of molecules. What is this? This is Avogadro number. So the kinetic energy of 1 mole of gas is Ke(m) into NaV. So this becomes F by 2 kT into NaV. If I have to write the expression of F, I know, sorry, K. So K I know, that is Ra by NaB. I have to check. So Ra by NaV. So this becomes F by 2 Ra by NaV into NaV to T. So the kinetic energy becomes F by 2 RT. So this is for 1 mole of gas. So this is the kinetic energy of 1 mole of gas. So now we can generalize it for the n mole of gas. So kinetic energy of n mole, so this is for 1 mole, is n F by 2 RT. So I want you to understand and keep all these expression in mind. So all the expression that we have obtained are, so kinetic energy of 1 molecule is F by 2 kT. Kinetic energy of 1 mole of gas is F by 2 RT, and kinetic energy of n mole of gas is n F by 2 RT. So this we have derived till now. So I have a question for you on this. So can you find the kinetic energy of 1 by 8.314 mole of hydrogen at 300 Kelvin. So let's take some time. So just try this before I discuss this, or you can pause the video and see this. Try it by yourself and then. So the solution to this question is, so the kinetic energy we need for this amount of mole for hydrogen. So first, the important thing we need to know for hydrogen is what is the degree of freedom. So degree of freedom for hydrogen we have discussed for the polyatomic gas, that is 5. So kinetic energy is n F by 2 RT. So n is 1 by 8.314 into 2. F we know that is 5. and R I already told you that is 8.314 joule per mole per Kelvin. That is 8.314 joule per mole Kelvin into 300 Kelvin. So the answer comes out to be 2.5 into 300 joule. So this is mole. So here I am writing this amount of mole is there. So mole will cancel, Kelvin will cancel. So this 750 joule of energy. And that is also the internal energy of this molecule. So with this we arrived at the concept that the total internal energy represented as U of an ideal gas is n F by 2 RT. And this U is a function of temperature, because this is constant, this is constant for a gas, all are the constant, only the temperature is the variable, because you can vary the temperature and you can see the internal energy of the gas changes. So the change in internal energy with temperature can be found out as delta U to be n F by 2 R delta T. So if you change the temperature, you will get the change in the internal energy of the system. So now we need to understand this, that when we have a molecules inside the system, then the only way to increase or decrease the internal energy of that gas in a system is by changing the temperature of the molecules. So if you increase or decrease the temperature, there is a change in the internal energy of the system. Okay, so now I have to tell you few things about internal energy. So internal energy, it, as we have defined, it is the total energy of the molecules present in the system. In general, it is the sum of kinetic and potential energies of the molecules present in a system when it is at rest. So that is the internal energy. Another thing to note about internal energy is that internal energy is a state function, not a path function. So what this statement is conveying is that the change in internal energy, if I write, then it only depends on the final and the initial state of the system. So it means that it only depends upon the final and initial state of the system. It does not depend on the path it followed while reaching from one state to another. So if I have to plot let's say I have to plot some PV diagram and it follows this path. This is at I initial state and this is the final state. So either it follow this path or this path. The total change in internal energy between the initial and the final state is just this. So this is the so we have made a foundation of what internal energy is. At last, if I have to know, if we take a isothermal system, then can you tell me what is the change in internal energy if it is going from one state to another? So in case of isothermal system, if I have to find the change in internal energy, F K R delta T. So because we know in isothermal system there is no change in temperature and hence there is no change in internal energy for the case of isothermal system. So next time if someone will going to ask that if there exists a system where there is no change in the internal energy, then we can say that there exists a system and that is the isothermal system, because there is no change in the temperature and so there is no change in the internal energy. So we have made the concept of internal energy very clear and how it depends upon the temperature and the concept of first law of thermodynamics that we will be going to discuss in the next class. Thank you.